All right, so for the first few lessons of our class, we'll be thinking about search. Formulating AI problems as search involves distilling the problem into a particular organization. To go over these concepts, we'll use a running example of the Rubik's Cube. So it's one of these. And let's think about the Rubik's Cube first before we try to generalize it to the general search problem. So this is a classic puzzle that I'm sure all of you have seen. This is a MathWorks form of the Rubik's Cube to try to sell you MATLAB. But the goal is to get to this state. The goal is to get to the point where every side of this cube is the same pattern. In the classic Rubik's Cube, it's the same. You try to get it to be the same color. And to get to that goal, you have the ability to do these moves. You can rotate slices of the. I want to be careful not to mess up my solution. You can rotate slices of the cube. And the tricky part is that when you rotate one slice of it, you're forced to sort of move the whole slice. And so if you want to get this color to go over there, you do that, and you get all these other colors to move as well. And so that's what makes it challenging, right? And so this is a great example of a search problem because a search problem is one that has many states. So there's a bunch of states, and here in the Rubik's Cube example, each of the states is all the different configurations we could have. All right, I'm scrambling this now, so hopefully I get this video done in this take because I'm never going to be able to solve this again. So all these are the different states that you can get to, right? And then in the search problem, you also have transitions or actions you can take. And so each of these little rotations, slice rotations, is one of these actions, right? And what happens is when you take an action, you transition from one state to another. Okay? And in addition, search problems can often have transition costs. In this case, for the Rubik's Cube, the transition cost is pretty much 1 no matter what. Although if you really want to get fine-grained and you want to solve this as fast as you can, then certain rotations are more natural. Sometimes you have to try to rotate the middle slice, which is a little bit harder. So that could cost you more time. So you could imagine attributing a time cost to the different actions you can take. But roughly, we can think of it as just all the same cost. So each move is one unit of time or effort, and then and so they're all unit cost. So a really nice way to think about search problems is by using the graph formalism. We can think of all the states as nodes in a graph and all the possible transitions as edges of the graph. So for example, here's a simple graph from the textbook of a simplified vacuuming world. All right, so in this vacuum world, there are two squares, the left and the right, and the robot's goal is to clean both squares. Right? And the robot has the ability to move left or move right and to suck. So if we're in this state on this top left, this state right here, then we are, we're able to move left, which means we'll do nothing because we're already in the left state, we're already in the left square. Or we can move right, which transitions us following this edge over here to this state of the world right here, where the robot's now in the right square. Both squares are both dirty, so we didn't really do anything other than move. But then we can also, from this original state we're considering, this left state, we could activate the suction of the vacuum, which would clean up the square that we're in, right? So we follow the S edge, which is for suck, and we clean up that square. So now we're in this state right here, where now we have the robot's still in the left square, but the left square is now clean. So this is the way to really organize our thoughts again, about the world that we're traveling around in while we do our search. Okay, and another way we can think about things is that if this state is the initial state, then our goal is to get to one of these guys, right? Our goal is to get to one of these clean situations where both squares are clean. So what we're really doing is like a pathfinding algorithm, right? We want to find the path that goes from here to here, right? And so that should give us some clues as to how we should think about these things. Now, of course, more complex search problems are harder to visualize on a page, But it's easy to sort of look at this and extrapolate that how useful the graph formalism is for thinking about search problems. So if we have this nice representation of a search problem, how do we find a solution? So how do we find that path to the goal state that I just drew in red? So if you learned about shortest path algorithms like Dijkstra's algorithm, this might look really familiar. In fact, if you have the full graph like we just saw on that page before, you could just run Dijkstra's algorithm and you'd be done. But in AI, or in AI problems, we often can't see the entire graph. This is one of the key things that makes AI a little different than other parts of computer science. So think about the Rubik's Cube. Right? As a human, if you look at this thing, with your amazing human level intelligence, can you stare at this thing and map out all the states and all the transition between the states? I mean, the answer is no, right? You can't. You don't have the mental capacity to understand the entire state space of this thing and all the transitions between all the states. So instead, what we can do is we can look at any individual state and easily sort of try different actions and see what happens when we try these actions. And so AI search problems are basically like shortest path algorithms where you don't get to see the whole graph. And AI search algorithms will therefore be somewhat similar to shortest path algorithms, but have this important difference. So let's think about what a search algorithm is able to do. So what it does is it starts at some state, and this is just the inputs to the problem, and this is what's referred to as the initial state for obvious reasons. Okay. Now from the state, you can always see what actions are available. So that's the assumption, is that whenever you're in some state, you can look and you have some function that tells you what actions are available. So in this case, let's say there's 4 actions available. But let's simplify that. Let's say there's 3. Okay? And then what you're able to do as a search algorithm is you're able to take one of these edges, take one of these actions, discover a brand new state, and what actions are available there. Maybe there's only 2 there. Okay? And so then you can continue expanding nodes, and this is referred to as expanding nodes, like I just suggested. So this is when you follow the path and you discover a new state and discover what actions are available. That's called expanding. Let's put it right here. All right, that's expanding a node. Okay, and what you're doing is you're going to find new states by following actions, and maybe in this case, maybe we backtracked to here and discovered and tried another action from the state that we'd previously been, or we might backtrack up here and try this action that was available, that we knew was available, but we didn't take it initially. We might backtrack and take this action, discover these states. Maybe this is only one option, so you continue down and try that. And maybe there's no actions here, maybe you're stuck. So this way of exploring, what you end up doing is you end up building something that looks like this, which is called a search tree. So this is a search tree. All right, that's a search tree, and it borrows terminology from standard computer science views of trees, which is that here this is a parent. This is a child, and here, this is a parent, and these are the children of the initial state, and so on. So, we can think about ancestors and descendants, just like in standard tree analysis. Okay, so one important concept that I almost forgot to add, which is why I'm adding this extra little video bit in, is that when we look at this tree, as we expand it, as we're doing what I was just doing, which is just like sort of going from state to state, looking at what actions are available and deciding which actions to take. These actions, oops, let me mark this in a different color. These actions that we've discovered but have not yet have not tried yet, that's called the frontier. People have also called it the fringe. I think those are the two most common terminology for this concept, and it's obvious why that is, right? We as a search algorithm have fully visited these states, have discovered exactly what what's happening in that state, whether it's a goal state. We know what actions are available at that state. But for these sort of actions, we know that some state exists if we take these actions from these states, right? But what we don't know is what's beyond that. Right? So that's why it's called the frontier or fringe. Okay, and so let's look at let's think about this tree and think about what's a really simple strategy for searching the tree. And it's kind of close to what I was just doing. Actually, let me just draw it all over again. So we'll erase everything. Okay. Blue. Okay, so we start from an initial state. This is the initial state, and we discover that there's I have 3 possible actions. So this is my search strategy that I'm proposing to you. You look at the states, the possible actions, and you just randomly choose one from them. Let's randomly choose this one. We expand this node, right? We expand this node and discover those 2 possible actions. So now let's just think about what is our frontier now. Okay, so our frontier is this one, this one, this one, and this one. Right? Those are the actions that we can take that we don't know where we're going to end up if we do, but we know that they're available to us. Right? So we can always backtrack and take that. Okay, and what we can do is then again randomly. This is my proposed search strategy. Is you start from the current state, you randomly choose one of these actions, and I randomly chose that one, and now I've discovered this state, and maybe there's one option, so you randomly choose that one, and then maybe there's 5 options, and you randomly choose this one. Okay, so this is the strategy. So what do you think about the strategy? It's pretty dumb, right? It's basically here. Let me show you what the strategy looks like with the Rubik's Cube. So this is the Rubik's Cube. We have I think 9 different slices we can rotate, and so randomly I'm going to rotate this one. Okay, now I'm going to randomly rotate this one. I can't even do it. And now randomly rotate this one. I mean, it's ridiculous, right? But if I just continue doing this, I mean, eventually I'm actually going to land on the solution. And that's sort of a weird aspect about this strategy that I'm describing, is that for many problems, in particular ones that have a finite state space, it's actually guaranteed to succeed in the sense that it will eventually land on the solution. But that can't be good enough, right? Like we need to think about ways to characterize search algorithms that will differentiate good search algorithms from bad search algorithms, like this random search one. And so what we're going to do is we're going to talk about 4 different aspects of search algorithms, of their quality, of their performance. Okay? So the 4 different aspects are completeness, okay, completeness, which is kind of related to what I was describing, is just that the quality of completeness is that the search algorithm will eventually find the solution if the solution exists. Okay, and you can imagine there could be search algorithms that will never find the solution. For example, a really, really dumb search algorithm, even dumber than the random search algorithm, is to try one action, undo it, and try that action again. Over and over again. And that's, technically it's a search algorithm. It's just a really, really stupid, really, really terrible one, and so it's not complete. But there are some smart search algorithms that actually don't satisfy the completeness condition. So we'll think about those later on. Okay, the second quality we're going to want to see in search algorithms is optimality. Okay, optimality means that the search algorithm will not just find a solution, but find the best solution. Okay, and when you think about, it'll either find the best solution or find the best path to the solution. So with the Rubik's Cube, if you look it up, and read about it on the internet or some other information source. I don't know where else you would look things up. It's actually solvable within 20 moves from any position, but it's really hard to find those 20 moves. And so people have written programs to do this, written AI programs, search programs to do this, and it's not easy, because I think if I remember correctly, the number of states is actually like 10 to the 17, something on that order. But you could a search algorithm that could discover the shortest number of moves, the smallest number of moves to get to the solution would be optimal. And then any algorithm that gives you a solution that's longer than that perfect solution, that really fast solution, is suboptimal or not optimal. Okay. The third aspect we're going to consider is time complexity. Okay. Time complexity is just the simple, the basic idea from computer science that we've studied in algorithms or in maybe intro to computer science, just like how, it's like a big O notation of, given how big the input is, how much data is in the input, how long does it take, how many steps does it take to reach the solution, okay? And the time complexity is really the biggest problem with the random search algorithm, right? Like I said, at infinity, if you try infinite random moves, you're going to land on the solution eventually. But pretty much it's going to take something on the order of the number of states, which again is 10 to the 17 for the Rubik's Cube, to get to land on the solution. So that's really expensive. Right? This is a tiny input, right? It's 3 by 3 by 3. This thing, the number of bits of information in this thing is really small, but the state space is huge. Okay, and then the last piece we're going to consider is space complexity. All right, so space complexity is, again, something we probably have looked at a little bit in basic computer science or algorithms. It's not often the thing that we think about when we design algorithms, because usually the algorithms that we study in school have pretty good space complexity, so we don't have to worry about it too much. But in this case, in the case of search algorithms, it can get pretty tricky, because again, if you're storing information about all the states that you visit, and you visit something on the order of the number of states, that can be super expensive, because the number of states can often be something exponential in the input size. Again, this thing 10 to the 17, or some huge number. Again, I don't have the actual number in my head, but it's a huge number of states. If you have to store even 2 bits of information about all those, you need more space than really is available to any computer right now. So we're going to look at these 4 things in the context of the different search algorithms we're going to be studying. So to start out, we're going to learn about 2 search algorithms called breadth-first search and depth-first search. And let's look at some pseudocode now. So this is a bit of pseudocode from the textbook for a general framework for search algorithms. In particular, tree search algorithms. There's a slight modification if it's a graph. But let's just look at the tree search because it's simple. So the idea is that the tree search algorithm just gets a problem as input, and it's going to return a solution. Okay, and the algorithm works like this. Right? First, you initialize the frontier. You just put you put the initial state of the problem in the frontier, and then you just repeat this inner loop. That's the whole thing is just in this one loop. Okay, so you loop this. Right? You say if the frontier is empty, then you fail. You say I failed. I couldn't find a solution. Okay, then the if not, if you didn't fail, right? You choose a node from the frontier. The terminology here is a little bit different than what I've just been describing it, but basically it just means you look in the frontier, you pick one of the states that you put in the frontier, and remove it. Okay, and how we remove it, or which one we remove, we'll get to that later. So so once you remove the state, what you do is the first thing you do is just check if that state is a goal. If that's a goal state, then return it and you're done. You basically found the solution. It's a little bit more nuanced than that because you have to return the path to the solution or how you got to that solution. But the idea is that you found the goal state and you're very happy. You won. Okay, but if that's not true, if it's not a goal state, if you haven't won yet, then what you have to do is you have to expand that node. That node that you just pulled out of the frontier, you expand it and you add all the resulting nodes from the expansion to the frontier. So what that means is, again, when you expand a node, what you do is you discover what the actions are that you can take and what the resulting states will be. Or sort of symbolic representations of those states because you haven't actually visited them yet, right? And so then those go in the frontier and you repeat. So what happens is then your frontier usually gets bigger initially because you're adding more and more states, but then eventually you'll reach a goal state if things are working right. Okay, so what's interesting what I mentioned a second ago is that how you choose which state to take out of the frontier is really important. And it actually determines a lot about your search algorithm and pretty much determines your entire search algorithm. And what we're going to talk about is two of the most basic search algorithms. So if you take out the first state that you entered into your frontier, so if it's a first in, first out data structure, then what you have is what's called a breadth first search. That means that you're gonna try to explore as many of the possibilities from closer to your initial state as possible, or closer to your current state as possible before moving on. Now, if your frontier is a last in first out data structure, meaning that when you remove a node from the frontier, it's going to take the state that you entered most recently, that you put in the frontier most recently. So this is something like a stack. Then what you get is depth first search, which means you're going to go as far as you can, explore as deeply as you can before backtracking. Right? With breadth first search, you basically have to backtrack because what you do is you try one action and you backtrack, go back to the previous state, and try a different action from that state. Okay, so let's look at these on the board. All right, so let's think about now what happens, how we implement these. All right, let's try to see what happens with these different search algorithms on this simple search tree. So I've drawn this out. The initial state is here, and there's two options, and then there's two options from this state and one option from there. Okay, so pretty straightforward. So let's start with the breadth first search algorithm. Okay, so that's the one where we're going to do first in, first out. Yeah, first in, first out. Okay, so we start at the initial state, right? I'll draw like that. And we discover, on our actions that will take us to these states. So our frontier is going to look like this. Our frontier starts like this. It's got B and C. Okay? I need to draw this. So first in, first out, well, this came in first. So the direction of the cube is this way. So we're going to take this one off, cross it off, we remove it from our frontier, and we go to expand it. So now we go here. We go down here, and we discover now D and E. So we add to the first in, first out data structure, which is pretty much going to be a Q, D and E. Should I do that right? Yeah. Okay, and then we continue. Right? The next step is take something out of the frontier. So it's going to be this one. Take C out of the frontier, and we go to that node. So we go take this action, and we end up here. Okay, and then we want to add. We discover what the next possible states are. By taking this action, we can get to F. So we add F. Okay, and we continue. And then we go to the next state available in our queue, and we take out D. So we end up here. There's no states to discover. This is a leaf node. maybe this is a goal state, maybe not, doesn't really matter for this exercise. And then we continue, we take the E out, we go here, and then we eventually take F out, okay? So this is what happens, right? And so what we went, the sequence that we visited these nodes was A, B, C, D, E, F. Now that's no coincidence that it turns out to be the alphabetical order, because I happened to write this out in level order. And that's what it looks like, right? And if you think about, or that's where the name comes from, right? It's doing a breadth first search, meaning it's going to find everything in each level before it continues farther away. Or if you think about this in a graph, it's actually easier to see. So in a graph, you have different directions, different edges, and maybe there's connections between your neighbors, and there's more nodes out farther. And even there might be connections to multiple, like that. Okay, so breadth first search would start at some initial state and then try all the one hop neighbors away. Right? It would try one move this way, try one move this way, try one move that way, try one move that way. And then it would continue expanding out. And if you think about this, if you zoom out even further, this sort of looks like this. It sort of looks like you're trying out everything there, trying out everything there, and so on. It's not exactly doing that. It depends on sort of the structure of the network, or of the state graph. But that's sort of what's going on. Okay, so that's what happens when we use first in, first out. Now, if we repeat the same exercise with a last in, first out, a stack, let's see what happens. Well, you should know what happens, right? We get depth first search. That's what I just told you. But what we'll see is, let's try to visualize it, right? So again, we start at the initial state. We expand the initial state, discover that B and C are possible states we can get to through these actions from A. So we add B and C to the frontier data structure, which in this case is a stack. So with the first in, last in, first out data structure, I'm going to draw it like the classical stack example. So we're going to throw things into the stack and pull them out from the top, or pop them off the top. Okay, so we start with A at the initial state, and we go to, we discover that we can go to B and we can go to C. So we're going to throw in B, we're going to throw in C. So C is at the top of the stack. So we're going to take that out, we're going to remove C, and we go to it, we revisit it, and we expand it. And when we expand it, we discover that we can now visit F. We can now reach F by taking an action from C. So we add F to the frontier, and now it's at the top of the stack. So the next step is we pop off the stack, and we get that we go to F and visit F. Okay, and then we discover there's no more states to visit from F, or F has no states to get to other than C. Maybe you can backtrack, maybe you can't. But the point is, there's nothing else to add to the frontier. So instead, we are going to take whatever is left in the frontier, whatever is on the top of the stack, which happens to be B in this case, right? It's B. And what we get is then we visit here, and we expand B and discover we can get to D and E. So we push D and E, and now we are going to pop off E, and then find that there's nothing to add, so we go back to the frontier, and we pop D, and we go there. Okay? So the order that we visited things in, if I did this right, is A, C, F, B, E, D. Okay? And it looks a little weird, but what it's basically doing is just following a path and trying to go as far as it can until it can't go any farther. And then it's going to backtrack. Only then does it backtrack. Whereas with the breadth first search, it backtracks right away. Okay? And repeating the same exercise, let's just think about what that looks like on a graph. So if we have a graph, let's do this. So you start at the initial state, you go to one of your descendants or one of your children, and then you keep going. Okay, and then now you can't go any farther, so you backtrack, and now you go to another child from there, and eventually there. I mean, it looks a little bit different, and it doesn't have as nice of a picture. In fact, one interesting thing is that if the graph is fully connected, right, in some scenarios where the graph has a certain structure, you can actually just keep following that branch, keep following that depth first search, and just visit every node. So, for example, if the graph is a grid structure, which can happen in some situations. So let's say this is the graph, right? And we start here. This is the initial state. Here's one possible depth first search order, right? You could expand this node. You discover this node and that node, but you expand this node, and then you expand this node, and then this node, and then this node, that node, that node, and that node, and you've never backtracked, and you visited every state. So sometimes things can happen that way. Okay, so that should introduce you to the idea of search algorithms, and there's a lot to digest here, I'm sure. So have a look at the textbook, and we'll go over some of these things in class. What we're going to try to do is we're going to try to analyze, remember those 4 aspects of search algorithms I talked about: completeness, optimality, space complexity, and time complexity. But we're going to try to analyze breadth first search and depth first search with respect to those 4 aspects in class. And you can read ahead in the textbook and see how the analysis is done. But we'll go through it together. So see you in class.